I just did or completed Andrew Ng's course on deep neural networks on Coursera. It was brilliant. And you build various neural networks in Python, but I'm not particularly good at Python. I'm learning. But so doing it in Excel was a really good way for me to see how it worked and understand it. And let me explain what this is trying to do. There are red and black dots, which you can clearly see are in two circles. There are black dots within inside a circle of red dots. And the function that you build, or the neural network that you build, is trying to spatially differentiate between the black and the red. And you forward propagate this function, and then you back propagate, and I'll explain that on the code. It's all happening on sheet, it's not in VBA. VBA is needed to kind of stamp the outputs, to increment through the function. So it's really just a stamp, and I'll show you where it's going, but everything else is happening in Excel. And as you can see, as it slowly moves through 90 iterations we're at now, I'm going to do 1,000. I've got a learning rate of 0.5. It's already starting to bite and force a function that's going to kind of hone in on just locating the black circle. So we should see a gap in the middle. If I just show you what that's going to look like, this is a PowerPoint of one I ran earlier. And you can see the curve beautifully drops off, and ultimately the function that is being derived, the machine learning, is differentiating the black from the red. It's learnt it pretty well over 1,000 iterations. Back in our model, it's getting closer at iteration 166. But I think the interesting thing is, if I just show you what this looks like in Python, it's disturbingly quick. So here's Andrew Ng's code. You go through and you load the various libraries, and this is the data set that I completely lifted straight out of Python. I put a red dot in the middle just to see what happens there. Here we're constructing the model, and I think he's used, or what have we used? It's a 3-layer model. It's not quite the same as mine. I've got a slightly wider model. And then you initiate the parameters, because they need to start from a certain place, otherwise it won't bite. I'm using the he-et-al, which basically takes account of the number of neurons in the previous layer to minimize the initial start point. That's what my parameters look like after initiation. And this is learning. So here is the Python version doing 1,000 iterations, which was about a second, 2,000. So I'm going to train up to 10,000. Yeah, I've made a 10,000 iteration. And once that's done, it'll do a plot. It'll show you the function that it's derived and how it fits the black dots and the red dots. And it's really good, 10,000 iterations. That's the learning curve, minimizing the cost function, and here's the actual plot that you get. So clearly, it's recognizing that this area, the function, as I said, everything within that circle is effectively a black dot. So back on the model, see, it's starting to inflect, and you've got this beautiful pattern of it closing in on the circle. I'm going to pause that because although it's fascinating to see how it learns, you might be interested to see how it closes in on this. But this is quite a fast progression, and every run is different because the initial state is different. So the base state in which the model, the neural network sitting, or the parameters for the model is random. So the way it trains itself to the ultimate function that differentiates black from red has a different starting point, but ends up at exactly the same result. And when I say the same result, it produces a function that differentiates black from red. Oh, look at this, it's doing well. But if you looked at the actual parameters, they'll be completely different every time. So the optimized function, the set of parameters will be different every time, but in combination, they result in a function that does this. I think that kink in the learning curve was where it breached, or the function breached the outer wall, and then just located all of the black dots. So obviously the cost function had a big step change because it caught most of the dots. Now, another 500 iterations to go. I'll pause this until something interesting happens. So only 30 iterations to go, and unfortunately the 1,000 iterations is not long enough for it to pick up this circle here and put an orange boundary around that so that you've got the donut shape. Probably because I shrunk the size of the internal circle. But anyway, that's finished, and it's gone pretty far. If I put another 1,000 iterations, operations, and it would really find that. But let me show you what's happening on the model. I've got the XY coordinates ripped off entirely from Andorang's course, and I've got the red and the black labeled in one, red in 0. Here's the little circle I put in the middle. This is just for charting, so I've got a cross plot. And then here we've got the first layer of neural networks, and it's basically y equals mx plus c. Here is the x, here's the m, and here's the c for these parameters, and that's case 2, case 6 or whatever it is. And that gives you a linear function, but you need to make that non-linear. So what we're going to do is put it into a ReLU, which is just making it non-linear. If it's positive, you see it. If it's negative, it just sets it to 0. That's the output of the first layer. Then we're on the second layer. The second layer is looking at the output of the first layer, and it's got its brain or its weights here. This is where all that information is stored. So these set of numbers on layer 2, layer 1, and layer 3, that's recording the function that differentiates black from white. So, sorry, I was looking at the backprop. If I actually look at the function, and then the activation function, which makes it non-linear, and then we come to layer 3. Layer 3 is looking at layer 2, so the input to layer 2 is the output. The input to layer 3 is the output of layer 2, and these are the weights, m and x. And then finally, we've got the activation function, which is a sigmoid, which is better for binary classification. Okay, so now we go to a cost function, or the loss, and the loss is basically just a fancy way of saying, what is it? It's a 0. What do we think it is? Well, we've done very well. We've got it with our function. If it's a 1, in this case, we've got 0.91. The model is giving us a 0.91 chance of that being it. And now we have to take the derivative of this backwards, and the derivative of the loss function is dead simple in the case of sigmoid. It's y minus y hat. That's the layer 1. If you look at the derivative of the weights with respect to dz, this is the formula. And then we go back up the tree and we keep working our way back. So this is the next derivative of the previous layer, and then there's the weights. And we work our way back up. Then we basically find the gradient of all of these functions. And because we're trying to minimize it, we work down the gradient. And ultimately you get to every step, you want to update the inputs with this value here. And this value is the previous inputs plus the learning rate times the gradient. Now, I've actually added a little bit more in this, which is one more step, which is momentum. And that just speeds everything up by having an exponentially weighted view of the gradients. So that if you've got a very fast learning rate, as I had here to speed this up, you want to look back over time, and I've set lambda to 0.8, so it's looking back at about five iterations. And it's averaging those out exponentially, so that if the sign is changing, the gradient is positive or negative, it will average that out. But if you've got a gradient that's running really well, then it will just it will sum those together, and it'll move more quickly. So it speeds up the process dramatically. Well, effectively that's it. I added a little bit of extra code momentum to make it quicker. I did it in Excel. You can see it's pretty quick. And I'm keen, if anybody else has got ways of improving on this, I'd be keen to see. I did this about 2 weeks ago, and I've since done a couple of MNIST digit classifiers and alphanumeric classifiers. And I'll probably put those up as well if people are interested. I would like to see more neural networks in Excel because they're quite simple to do. And it's impressive putting machine learning in Excel because it becomes